Okay, so you can see that today's lesson is on inverses of relations. Now, when we're given a set of ordered pairs like we are in this first example, finding the inverse is really, really simple. Let's start by looking at this box here. It says the inverse of a relation is the relation obtained by switching the coordinates of each ordered pair in the relation. Now let's go ahead and add this to the box as well. We're going to get to this a little bit later, but we can also say or by switching the x and y in an equation. Okay, so let's look at this first example. So we have this relation here, and if you notice, this particular relation is a function because there are no repeats with the x's. Each of the x's has its own unique value. So to find the inverse of this, just like this definition of an inverse said, we're going to switch the coordinates around here. So it's going to be this first coordinate will now become the point 2, -3. Now notice the -3, the negative stuck with the 3. Don't switch just the 3 and the 2. Take the negative with it. So it's going to be a +2 and a -3. And the next coordinate would be 4, -1, 3, 0, 8, 2, 7, 5, 8, 7. You get the idea here. Well, what they've done over here in this graph to the right is they've taken and graphed the original set of points, the -3, +2, the -1, +4. The original set of points, those are the ones graphed here in blue. The ones that we just came up with, the inverse, is what's graphed down here in red. Well, notice what we have here. This is a reflection. All of these points are reflected over this dashed line. This dashed line is the line y equals x. So this is super important, even though it seems minuscule. It is important to understand that all inverses are reflected over the line y equals x. Okay, let's look at some other information here dealing with what we've just done. So this next section is about finding the domain and range of a relation and its inverse. Remember, the domain for a relation is the set of x's. So the domain for this particular problem would have been -3, -1, 0, 2, 5, and 7. And the range would be the set of y's, the output value. So the range for this first example would be 2, 4, 3, 8, 7, and 8. Now look at our domain for our inverse and our range for the original. Notice that they're the same, which makes sense because if we switch the x and the y around, what would have been the range for the original function would now become the domain in our new relation. And if you notice for this particular problem, the original is a function because there are no repeats with the x's, but you can see here with our inverse, there's a repeat, there's 2 8s here, so that means the inverse in this particular example is not a function. So let's look to see what they want us to put in these boxes down here. It says, consider that an inverse is found by switching the coordinates, and consider that the domain is a set of x coordinates and the range is a set of y coordinates. Therefore, it makes sense that the domain of the inverse is the same as the range of the original relation, and the range of the inverse is the same as the domain of the original relation, okay, which we just illustrated up here. And like I said, it does make sense because you just switch the x and the y, so the domain and range are also switching by doing that. Now, just like I just talked about, the inverse of a relation is always going to be a relation. Remember, a relation is just basically any set of ordered pairs. So a set of ordered pairs is always going to be a relation, but a function gives it a separate status. It gives it, makes it so it's going to be its own unique thing. So what this is saying is that just because the original is a function doesn't mean that the inverse is also going to be a function. Just like we noted with that previous example, because there are repeats in the inverse in the domain. Okay, let's look at another example, this time dealing with the graph. So it says, consider the function with the domain of the set of all real numbers in equation y equals x squared. So remember, the graph for y equals x squared is going to be the shape of a parabola with a point 0, 0. When I put 1 in for x, I'm just coming up with a simple graph here. When I put 1 in for x, 1 squared is 1. When I put 2 in for x, 2 squared is 4. When I put 3 in for x, 3 squared is 9. That's going to bring us up here. And remember, with a parabola, it's reflected of the line of symmetry, which in this case is the y-axis. That's good enough. Okay, so there's our parabola for the equation y equals x squared. Now it says, what is an equation for the inverse of this function? Well, if I switch, like we said in this, remember the second part of this box, it says if we have an equation, we're going to switch the x and the y. So to find the inverse of this, I'm going to switch the x and the y, so it's going to be x equals y squared. And to graph that, I'm going to make a table over here. Well, we don't need to make a table. Well, yeah, let's go ahead. If you notice, this time our independent variable is y, because it's saying to find x. We're going to take and square the y. So I'm going to put values in here for y, like -1. Let's start out with -2, -1, 0, 1, and 2. When I do that, when I put -2 in here for y, I get a +4. -2 squared is a +4. When I put -1 in here for y, -1 squared is a +1. So these are going to be the values I'm going to graph. So when x is 4, y is going to be -2. When x is 1, y is going to be -1. When x is 0, y is 0. When x is 1, y is 1. When x was 4, y was 2. Or if we continued on, you'd see that this would be the shape of our graph. So we can see that this is the equation y equals -x squared. So we can see the two graphs here, and also you can recognize, remember what I said earlier, this would be the line y equals x. Oops. By the way, the line y equals x is pretty easy to graph. Just a diagonal line. You notice it goes through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. All of those coordinates, so just goes through the grid lines and going through the origin there. So there's our line y equals x. So you can see that these two graphs are a reflection over that line y equals x. Now it says in part C, is the inverse a function? Why or why not? Well, you can see that, remember earlier in the year we talked about the vertical line test to determine if a graph is a function or not. Well, you can see that if I draw a vertical line through this graph, it passes through 2 points. So the inverse is not a function. And you could say it fails. Just abbreviate the horizontal line test. Or you could even say that you look over here at our table of values, and our domain, or x, has two different values for y. So we have a 1 here that's got a -1 and a 1 that's got a value of a +1. So it is not a function. Okay, why don't you guys go ahead and take some time to graph this next equation. By the way, when you set up a couple of you really We're only going to have about 4 points that'll fit on this graph, but why don't you guys go ahead and pause the video and then start it up and after you have it finished to check your answers. Okay, so you should have done this. It says we have the original equation is y equals negative 2x squared. It says what is an equation for the inverse of this function? Well, all we have to do is switch the x and the y. We don't have to do anything else for these particular problems. So when we switch the x and the y, our inverse is going to be x equals negative 2y squared. Then it says graph the function and its inverse in the same axes. So the original function, let's do x just to make it easy. Well, the original function is pretty easy. If you put 0 in here for x, obviously you're going to get 0 as your answer. If I put 1 in there for x, 1 squared is 1, times negative 2 is negative 2. So when x is 1, y is going to be negative 2. And now when we put 2 in here for x, 2 squared is 4, times negative 2 is negative 8. And if you notice, my that's going to run off my grid here, but that's okay. 6, 7, 8 would be right about here. Reflect that over the y-axis. And we have our parabola, which, wow, that turned out pretty good. Okay, so now we're going to graph the inverse. For that, you might find it easier to do the xy table. Again, this time our y is our input. It's our independent variable, so we're going to pick values for y. So I'm going to pick, let's just pick negative 2, negative 1, 0, 1, and 2. So if I put negative 2 in for y, negative 2 squared is a positive 4, times negative 2 would be a negative 8. If I put negative 1 in for y, square it, you get a positive 1, times negative 2 would be a negative 2. If I put 0 in there, I'll get 0. If I put 1 in there, 1 squared is 1, times negative 2 is negative 2. And this, when I put 2 in there for y, I end up getting negative 8 as my answer for x. Okay, so now let's graph these on the same grid. Again, my negative 8 isn't going to fit, but we can eyeball it. It's negative 5, negative 6, negative 7, negative 8. Negative 2 would be down here. Then we have negative 2, negative 1, 0, 0. And then we have the reflection here, negative 2, positive 1, negative 8, positive 2. Oops. Again, just like we've already noted, there's our line y equals x, and it's a reflection over that line still. And to answer part C, it's not an inverse. Okay. So as you can see, it can be a real pain to have to figure out whether the inverse is a function by sitting here and graphing them all. There is an easier way to figure out if, by looking at a graph, if the inverse is also going to be a function without having to graph it. To do that, why don't you watch the next video.